morning. It's a beautiful day out. I wanted to talk today about tube testers, a little bit about how they work, some of the differences, and I'm going to go over the Jackson 648 as I already had done a video on that particular unit. But we're going to look at the schematics and look at the circuitry and see what's exactly going on inside. Tube testers really basically are simple, but I haven't had a chance to look at one of the top end ones yet to see what's going on there. But we're going to focus on the Jackson, and I'll show you some schematics for the Jackson, and we'll go through those. And also I have simplified circuits that I drew up for each function, so it'll make it a little easier to understand what's going on inside. But there are three basic types of tube testers: emission, dynamic, and mutual conductance. An emission tester kind of gives you a go no reading test of a vacuum tube. In other words, can it actually function or not? That's, back in the day, guys going out on service calls, that's what they needed to know, whether a tube actually functioned. An emission tester ties tube elements together and treats it like a rectifier. A dynamic tester, sometimes called a transconductance tube checker, like the Jackson models that we're talking about, simulate an actual tube circuit connecting the tube elements like they might be in an operational circuit, putting actual signal on a control grid G1 and a voltage on grid 2. It uses AC voltages for testing. And this particular type is far better than a plain emission type and can show if a tube is closely matched to another also. But transconductance is a measure of the change in plate current to a change in grid voltage, with the plate voltage held constant. The third type, which a lot of us are familiar with, is a mutual conductance tester. Now, it also connects the tube elements in an actual circuit, but it tests with DC voltages and also a separate bias voltage, and also gives a direct transconductance or GM reading, which is expressed in micromhos or MU. So you can see that it's the better of the three, while the Jackson is far superior to a basic emission tester. So let's look at what goes on inside the circuitry of the Jackson 648.
First, I want to go over the controls again on the Jackson 648R. Most of the models are very similar. The circuitry is almost identical inside, but the layout is a little different. The plate control, of course, sets your current, the filament for the filament voltage, leakage test up to 2 megohms, shorts test mode you use when you're actually testing the tube, and shorts test for cathode plate and the grids. The life test lowers the filament voltage, and as you hold it, because it's a momentary switch, if the meter starts dropping appreciably, then you know that that tube has less life in it. And the line control. Let's talk about the line control setting first. First thing you want to do when you get a hold of one of these is, on a level surface, you want to adjust this little screw here for the meter, because zero reading, because if the whole unit is tilted either way, this can sit in another position. But the manual suggests setting the line control with the setting at 100 and then working from there. So if you have a variable supply, that's fine. If not, you can do it at 120 to get the line in the middle. So according to the manual, you'd set it at 100, and we're going to adjust the adjustment on here so that we get the needle right in the middle on the line setting at 100 volts. Again, here's the inside. The switching is most intimidating because I don't know how the engineers ever figured this out for the thousands of types of vacuum tubes to be able to switch in all the different elements for testing and switch in the different resistors required to load test that particular tube. But this R5 is the calibration test, the setup for the calibration of the plate, and this is your line control. Now, the easiest thing for calibration is go buy yourself a calibration tube unless you have a variable voltage and variable current power supply like I have, where you can actually set the milliamps and then make your adjustment. But you can purchase from Vacuum Tubes Inc. or on eBay. You can get a calibration tube, and it's real simple. Just pop that tube in and set the switches for the settings you need, and set this resistor here till you get the correct reading on the meter. And to adjust the line voltage, once you are set for your 100 volts, you just adjust this resistor here so that you get as close as you can to a center reading on this particular meter. But let's look at what that does in the circuit. Pretty simple. First, I want to talk about the banks of switches there. And these switches, if you notice, these are the same switch, different segments of that switch, but they all move. The top ones, which are the row E, circuit E, and the bottom row is circuit D on the front panel. So when you would depress a circuit E switch, all these segments move together and contact these contacts that have the arrows. So if 6 was pushed, notice this segment would be all the way up contacting this contact here. So the same works with the TET switches, the UV, X, Y, and Z. But during line calibration, all these switches are at their default. So you would have the line power on and the switch set for 100 volts. And if you come off this transformer here on the 30 volt, if you trace the circuit, it goes down through X, through Y, Z, back up through W, and then through the bottom of U, and right up to one side of the meter. And they call the common negative on here that they're using minus. It's actually the common in the whole circuit between the transformers and everything. Goes down through R15, which is your line adjustment, through D1, R16, through UV, W, Z, Y, X, back up through U again, and then to the meter. So you would just adjust your R15 for center line, and that's it. That's all it is for calibration of the line voltage. And once you do that, you really don't have to do it again. Let's look at what that's actually doing in the circuit. There are two ways this is wired on the schematic. If you look at this schematic, this is the 648R. Do you notice how D1 is taken off the center connection of the potentiometer on R15? But the models previous to 648R, it's actually does the same thing. It was just wired a little different, where they have the diode on this side of R15 through R16, and these were those test switches that it feeds through, and the meter was connected directly to the potentiometer wiper. But the 648R, which I have, it's connected to the center is the diode and resistor through the test switches. I don't know why they changed it. but I don't think it really makes any difference on how it's done or how they do that. So let's continue on and look at the next thing. So let's look at the test setup on how it tests a 6L6 or a 6V6. This is the schematic for the 648R, which is basically the same as the other 648 series, just different tube sockets and a few other enhancements. I have these all colored. We're going to be using this particular socket over here, the octal socket, and pin 5 is grid 1, pin 4 grid 2, pin 3 the plate, cathode is pin 8 over there, pin 7, pin 2 are filaments. So we're going to have switches 1, 2, and 3 depressed, and switches 4, 5, and 6 on the lower switch bank pressed. So let's follow these out and see what's happening in here. So if we go to 1 here, and 1 corresponds to pin 2 filament. If we follow that, when this is depressed, the segments slide up and we see the connection that it makes, and it goes to the common, minus, ground, whatever you want to call that connection on the transformers. So one side of the filament is connected to common through this switch. We go to the next switch, number 2, which is pin 7 filament, and it runs up when this switch is depressed, and we follow it through where it's going, the circuit, and B isn't depressed, so it goes straight through, and we go up to our filament selection, which would be at 6.3 volts. So number 3 corresponds to the cathode, which is pin 8. So if we look where number 3 goes, through the switch, through switch number 2, through switch number 1, and C is not selected, so it's in its default position, through switch B, and we follow the line down, and we go to the test switch, short switch. Now in the test mode, these 4 connections here connect to this row. We have the cathode connection connects to this connection. The plate in test mode goes there. Grid 2 goes there. Grid 1 goes there in test mode. These switches are all closed there. So if we follow this back up and we follow the orange line again, it brings the cathode pin 8 to common or ground. So the next switch is switch 4. Now switch 4 is on the lower bank, which is selected. So the connection 4 is grid 2, or the screens in a vacuum tube. And if we notice, this switch isn't selected, just the one on the bottom row. So circuit goes down through to the bottom switch, goes straight through 3, 2, 1, and C and B, which aren't selected. They're in their normal off state. And it comes down through the plate, which is the green, is what we're following, number 4, and goes over into here. And it kind of gets a little tricky. That's why I think it's pretty dang amazing of how they figured out these switches arrangement, these engineers back then. No computers or anything, but There must have been a lot of trial and error. So it goes up through X, Y, and Z, which aren't depressed, up through here. Now W is the test switch for this particular tube, which is going to engage the voltage to the plate. So this switch would be pressed, this segment would be slid up, connecting to the contact, which is here. And if we follow it down, it's going through R6, puts it in the circuit, and R4. And if we follow back through R5, R4 is the plate potentiometer. R5 is the calibration potentiometer. And if we follow it up again, it splits off to two places. It goes through U, which is not depressed, up to one side of the meter. Then the other goes this way through V, and remember now W is pressed, so this segment is slid up and connects it to 225 volts on the plate. And also, the circuit connects this way through R3, R2, R1, and resistor R, back up through U, to the meter. I'll show a simplified schematic next of that. It's pretty simple how it is, but the switch arrangement boggles my mind and how they figured it out. Let's look at how simple this really is. And that's it. That switch bank switches in the required resistors, which in this case is R, R1, R2, R3, and R6 for the 6V6 or 6L6 selection. So we have 225 volts coming in here through R11 to G2. Now the G2s always get the same voltage, which could be 225, 50, 30, I think 100. It depends on, let's go back and look at the schematic here. We have 225, 110, 50, or 30 available to put on the plates of the tubes. And the filaments receive, or the signal on the grid is 5 or 1 volt. And if we follow this particular connection, which is 5, that's grid to the screen. Remember I said all the screens feed the same amount through the same resistor, but it depends on what the voltage is set at on them up here. So in this case, we follow through. It's going to go down through the bottom switch, which is activated, through 4, cross through these switches, 321 CB, and through the switch and test position, and back through, there's our R11, and it's picking up the connection there, which again, this is going to the 225 volts. And number 6 is the control grid. We look, 6 goes to G1, and if we follow that through this segment, through this switch which is activated, down through this switch which is activated, and through number 4 which is activated. You see how complicated somebody had to figure all this out. And goes this way, and then through B, A. If we follow it down, we're back to the grid. And we're going to head up here. We're going to go through A, and if we notice, it takes us to 5 volt. So it puts a 5 volt AC signal on the grid for testing. And the Setup for the 6V6 and the 6L6 is exactly the same. It switches in these exact same resistors. The only difference is the plate potentiometer is set for 25 for the 6L6 and 35 for the 6V6. Now what happens here is, of course, the 6L6 draws more current through the tube. So what happens when the 6L6 is selected, we're more counterclockwise, so you actually have more current shunting this way and less current shunting through the meter to get your reading. Now for the 6V6, it's more clockwise than the 6L6, so the current will be less going through the 6V6, so you'll have less current through this shunt going this way, and you'll have balanced more current this way to compensate for it. So this is just actually a shunt circuit. Pretty simple on how the tube's tested. And the nice thing about the 648 series is that because they're actually putting a tube in an actual circuit, where a lot of the other testers for emission, they actually tie all these elements together and do a test. Well, here it reproduces some actual conditions. Next, we're going to look at the shorts and leakage test. We'll start with the shorts, but to make it simplified and make it a little easier to understand on the schematic, the way they laid this switch out, I number these connections, these 1, 2, 3, 4, and 5. If we remember when I talked about the operation of the actual testing, the 1 position, these switches would connect to 1, this one to 1, this one to its 1. If you turned it to the cathode position, then this would connect to 2, the plate would connect to 2, grid to 2, grid 1 to 2, and so on with the plate, grid 2, and grid 1 connection. Now there's always 110 volts on this line on the other side of the neon indicator bulb, and there's also 50 volts on this line going to the resistor, and we'll talk about that in a minute. So let's look at how the shorts tests are actually performed. If we go over and look at the cathode shorts test. So as I said, normal connections in the test mode are each element to number 1, number 1, number 1, number 1. So if we look what happens when we put it in cathode selection, then everything is switched to row 2. Cathode plate, grid 2, grid 1. So to recognize a short, this line always stays connected to the minus or common. And it connects at this point, and in this wafer switch, all these are connected together where these lines, all these, you can see it where it shows. So if you have a short in your cathode, which this goes to the connection to the cathode during setup, and if there's a short, it'll go down through here. Now don't forget, if there's a short, this is connected to the common. So if you had a short and it would go automatically you have your voltage going down, neon light would light. You have a short to the plate, it's going to light because the plate is now connected to ground. Grid 2 is now connected to ground. Grid 1 is now connected to ground. So if you cycle through, if there's a short to each between the elements, it'll show. You'll get the neon indicator lighting. And the same with the plate short test. We're in position 3 on the switch now for the plate. The same thing. The plate runs over to the side of the capacitor. And if you have, and the ground or minus is connected this way, and if we see this, it runs up to 3 to the grid 1, so that's grounded. Grid 2 is grounded. And if we follow the wiring, then we see the cathode is grounded. So if there's a short, we get an indicator, and a short's indicator there. And so on, the same thing through the grid 2. Grid 2 connects everything to the number 4 position. And so on with the grid 1, connects everything to the number 5 position. So you have the shorts test mode when you're testing the tube for operation, then cathode plate, grid 2, grid 1. And then the leakage, that's another thing. Most testers put a neon indicator through a dropping resistor to test for the actual short. But this one has a neat little circuit here, and it actually will tell you if you have a high leakage in megohms on the tube where the others won't. Let's take a look at that. Now, this has an NE51 neon bulb in it. And there's a circuit here is actually how it's wired in the 648. And I'll tell you a little bit about neon bulbs. They're a little unique. You couldn't use an incandescent bulb in this situation because a neon bulb, this NE51, will start to light dimly at about 50 volts as the gas inside ionizes. At 60 volts, the gas is completely ionized, and actually across the circuit, it acts like a short, but it has with a dropping resistor, the current draw is only 0.3 milliamp or 300 microamps. But that's why you need the current limiting resistor in series with the neon bulb, especially like if it's connected across 120 volts, because it would just self-destruct because it acts like a short when that gas ionizes. So if we look at this, in this situation, this is where the tube elements are switched in. So if a tube element is open, you get a small current flowing from the transformer connection 3 up through R17, through R13, and back through R14 down to connection 2. So you have a 60 volts between this point and this point. And these resistors form a divider, voltage divider. If you were to measure the voltage across a neon lamp at this point with no short, we'd get about 18 to 44 volts depending on where R17 is set, because it would be shunting some of that through here with a higher or lower resistance. Now the capacitor in here serves a unique purpose. When a capacitor is charged, no current flows through it unless it is otherwise bad or leaky. You can have a leaky capacitor. So if we have an element shorted right here, the capacitor would charge, and if the neon bulb was removed at this point, if it wasn't here, you would see this capacitor charged to 110 volts from current from point A to, or point A, which is 1 on a transformer, and 3, 110 volts. But, and that would be between point B and C. But as the voltage rises across the capacitor, the neon bulb will fire and the voltage will rise to the 60 volts with a small current flowing through R14 between transformer port points 2 and 3. So once this capacitor charges, the voltage is raised up enough to fire this tube, and it turns on and stays on. Now let's say if we had some leakage here. Say we had a tube element and there was 1 megohm leakage through it. A normal tester that didn't have a leakage control wouldn't find that. And it gets interesting here. If R17 is set to the 0.25 megohm setting, a small current flowing from the transformer point 3 through R17, R13, and R14, which is the voltage divider. So also a small current flows between transformer points 1 and 2 through the 1 megohm leakage short, charging this capacitor. Now some of this capacitor's charge, because this is such a high resistance, is drained off through R14. And R17, let's say it's set over all the way over to 0.25, which this in fact would be 0 ohms because the wiper would be shorted to this point. That keeps the voltage limited to 30 across the neon lamp at this point, because you have less resistance here. You only have 220K now, and that keeps the voltage limited across this to 30. But if R17's resistance is increased to 500,000 ohms, now that would be on the leakage control at the 1 megohm setting. The voltage across the neon bulb rises to about 52 volts, and the lamp will light really dim. And that indicates a 1 meg resistance short in the tube element, or between 2 tube elements being tested. So this can actually sense up to a 2 megohm leakage from 0.25 to 2 megohm, and you'll get a dimly lit or flickering NE51, the neon bulb, to tell you that you have a little bit of leakage there. So that's about that for the Jackson, the 648 series. Other than the newest one, I think was made in 1969, that was the 648-1T, and it actually will check for gassing and has a little solid state circuit, which I've been thinking about possibly building a PC board for that could be used in any of these 648 series with one switch added, and you could actually check for gassing in any of the 648s with that circuit.
So there you have it in a nutshell, the operation of the Jackson series of tube testers, all except for the last version, the 648-1T, which had a FET transistor circuit in there for testing on gassing, which is also important. Some of the better tube testers have that option to test for gassing. I've been thinking about recreating that on a PC board that could be added to the Jackson's 648 series testers. You'd only need the board and one switch to switch the circuit in and out. So I might do that. But if you have any questions or comments, give a yell. Have a good day.